Okay, let's dive right into this explainer. Today we're looking at something that honestly feels straight out of a sci-fi novel, but it is entirely real. We are talking about extracting pristine, drinkable water from literally the driest skies on Earth.
And to really grasp the massive scale of the opportunity here, we've got a mind-boggling number to kick things off. 12,900 cubic kilometers. That is roughly the amount of water just floating around in our atmosphere at any given moment. To put that colossal number into perspective, think about all the water in every single river across the globe. That's about 2,100 cubic kilometers. So atmospheric water completely dwarfs our global river water. There's nearly 6 times as much water floating above our landscapes as there is running through them. Which, when you think about it, proves exactly why we absolutely need to be looking up for our future water security. Section 1. Water from desert air. Right, so to prove this wasn't just some lab trick and that it could actually work where we need it most, researchers ran an experiment in Death Valley, California. Literally one of the hottest, most hostile, bone-dry environments on the entire planet. They took a lunchbox-sized container, left it out overnight, but here's the wild part. It was just a completely sealed box. No power, no batteries, no compressors, absolutely zero moving parts. Inside, there was just about a kilogram of a white crystalline powder called MOF 303. Left completely alone to face the elements. And by the very next afternoon, this totally passive setup had magically generated 210 grams of clean, liquid drinking water, literally pulled directly from the desert air without a single watt of electricity. I mean, how on earth did a pile of powder pull that off? Section 2. The accidental Nobel Prize. Let's move to and see how this builds. Because to understand how we pulled off this miracle, we have to look back at the incredible history behind this powder. A journey that actually just culminated in the 2025 Nobel Prize in Chemistry. The whole timeline kicks off back in 1974. An Australian chemist named Richard Robson was doing a classroom teaching exercise with ball and stick models. He just sort of wondered, hey, could you build real crystals with deliberate empty space? Flash forward to the 1990s, and scientists Susumu Kitagawa and Omar Yaghi independently turned that wild idea into reality. By 2017, Yaghi's team built the first water harvesting prototype, and by 2025, they're sharing the Nobel Prize. The field they basically invented is called reticular chemistry. Essentially, it's the stitching together of molecular building blocks into extended crystalline networks. We call these materials metal organic frameworks, or MOFs for short. Imagine like metal ions acting as the structural corners and long carbon-based molecules acting as the connecting struts. But the absolute most important part of these entire frameworks, it's the literal nothingness, that deliberate engineered empty space in between. Now, here is the beautifully witty irony of this whole story. Yaghi's team actually discovered this water harvesting miracle completely by accident. See, his lab was originally researching carbon capture, but their MOF frameworks annoyingly kept grabbing moisture out of the air before they could ever grab the carbon dioxide. And they were doing it in bone-dry conditions where, frankly, nothing else worked. So that annoying little nuisance, turned out to be the discovery of a lifetime. Section 3. The step function secret. And this brilliantly illustrates what makes the modern version so special. That original 2017 prototype used a framework called MOF 801, which was based on zirconium. Problem? Zirconium costs a staggering $160 per kilogram. Ouch. So, MOF 303 is the evolution of that. It's an aluminum-based version that brilliantly drops the cost to roughly $3 a kilogram. Now, the molecular structure of MOF 303 pairs up with a really vital concept called an adsorption isotherm, which is basically a graph that tracks how the material behaves at different humidity levels. When you visualize that chemical structure, it's really all about the pores. They are exactly 6 angstroms wide. And to give you a sense of scale, 1 angstrom is a 10 billionth of a meter, so tiny. This pore isn't just some bucket you dump water into, it's a perfectly sized molecular corridor. It quite literally forces 3 angstrom wide water molecules to fit inside, side by side, with practically zero room to spare. But the real engineering hero here is the step function behavior. See, normal desiccants, stuff that absorbs moisture, have a gentle, sloping curve. They take on water gradually, they form super tight chemical bonds, and you basically have to blast them with intense heat to release that moisture. MOF 303, though, it behaves like a light switch. Below 12% humidity, it holds almost nothing. But the second you cross that threshold into the 12 to 20% range, bam, it aggressively strips water from the dry air, filling up incredibly fast. Best of all, because the water is just held by weak physical bonds, not intense chemical reactions, MOF 303 easily releases it with just a super mild amount of heat. Section 4. The day and night engine. So, how do we actually use the step function switch in the real world without using any electricity? Well, it relies on a beautifully simple, completely passive cycle. It uses the desert's natural temperature swings as its only engine. Step 1, nighttime. The desert cools down, relative humidity naturally bumps up a bit, and our open box allows the MOF powder to basically inhale the water vapor. Step 2, dawn breaks. The box is sealed up, the daytime sun hits it, naturally heating the powder and easily driving the vapor off those pore walls. Step 3, since it's totally sealed, that vapor has nowhere to go but toward a shaded, cooler aluminum condenser. It turns right back into liquid, drips into a collection vessel, and you've got water. The desert itself is the engine. Section 5. MOFs versus hydrogels versus fog. Now, when we stack MOFs up against other methods, we definitely see some distinct trade-offs. Fog nets, for example, are practically free and yield incredible amounts of water, but they are severely limited geographically. They only work in specific seasonal fog zones, like the coasts of Chile. Then you've got MIT's hydrogels, much cheaper than MOFs, and they look super promising, but historically, salt-loaded hydrogels risk actually leaching those salts right back into your drinking water. Not great. MOF 303 undeniably carries a high upfront cost, but honestly, it is the undisputed king of bone-dry environments. It works flawlessly in extremely low humidity, producing pure water without polluting the output. Section 6, the commercial reality check. Now, what's really interesting to consider here is how we bridge the gap, because we know the basic science works, right? But we really need to ground the hype in reality. Omar Yaghi actually founded a startup called Atoco to scale this incredible tech, and they are moving way beyond that little lunchbox in Death Valley. Atoco has now developed 20-foot shipping containers capable of yielding 1,000 liters of pristine water a day, completely off-grid. And if you plug it into a power source, up to 4,000 liters a day. They're currently targeting places where traditional infrastructure just completely fails. We're talking remote data centers, field hospitals, disaster response zones.
But let's be super realistic about the commercial bottlenecks blocking mass adoption right now. First, the passive daily yield per kilogram of MOF is still relatively low. An average person needs about 10 times the water a passive kilogram produces, which means you need literal tons of this powder for a whole community. Second, there is a massive lack of toxic solvent-free manufacturing at a global scale. We just can't make it cleanly enough yet. And finally, you are competing against heavily subsidized, artificially cheap municipal tap water. The physics works beautifully, but the green manufacturing supply chain, it just doesn't exist yet.
To really put that economic hurdle into perspective, just think about this number, 10x. Researchers estimate that drinking atmospheric water right now would cost roughly 10 times what an average person pays for subsidized municipal tap water. That makes it a really, really tough sell for your average homeowner today. So the crucial point is this. We absolutely have to separate future infrastructure from consumer gadgets. If you're a homeowner wanting water security today, a cheap rain barrel intercepting a wet roof can yield roughly 60,000 liters of water a year in a moderate climate. The MOF harvester is serious future infrastructure. The rain barrel is available right now for pennies. I think this poignant thought really perfectly summarizes the current state of this incredible technology. The chemistry that took 50 years to invent is now waiting on a supply chain. These MOF frameworks aren't a fraud. They are simply early. This isn't some magical gadget you can go buy at the hardware store for your backyard tomorrow. It is a serious piece of global infrastructure that simply hasn't been fully built out yet. Which leaves us with this final, somewhat provocative question. When will our infrastructure finally catch up to the most elegant water engine ever invented? Because the water is definitely there, a massive reservoir floating right above our heads, and the day-night cycle is literally the cheapest engine anyone has ever found for driving it. We just have to build the factory. Thank you so much for joining me on this explainer, and hey, keep looking up.